Hello and welcome back to another fun and fun-filled episode. See, there's two funs there. And we're going to be looking at some generic trigonometric ratio problems. And the objectives today are use the sine, cosine, and tangent ratios to determine side lengths in right triangles, and use the sine, cosine, and tangent ratios to determine angle measures in right triangles. And everything revolves around SOHCAHTOA. And we'll remind you or tell you about what SOHCAHTOA means momentarily. In fact, before we even start looking at the ratios, the sine, cosine, and tangent, maybe we can look a little in depth into what SOHCAHTOA actually means, or what it stands for. It's an acronym. It says that the sine of a particular angle is a ratio of its opposite to hypotenuse. Now that means opposite over hypotenuse. So sine is the opposite over hypotenuse. The cosine, which I didn't write here, I should. The cosine is the adjacent side over the hypotenuse. And the tangent of a particular angle is the opposite divided by the adjacent, or the opposite over adjacent. So when we look at this example now, we have let a triangle ABC be a right triangle with acute angle A. So we're focused on this angle here, A, okay? So now what we want to do is look at the sides that are relative to the angle. Now, before we do this, let me just kind of go through a bit, and let me kind of show you how to work SOHCAHTOA. So right now, we're down here. So how to label your right triangle? And I advise doing it this way all the time. You can mix 1 and 2 up. It doesn't really matter. It depends on how you want to deal with things. But I try to stick to this because I will never mislabel a side. So it says, locate the hypotenuse by finding right angle. So here's the right angle. And look at its opposite side. So there's its opposite side. So then this segment AB is actually the hypotenuse. So what I'm going to do is I'm going to now label that in red. That's just hype. The next thing I'm going to want to do is I'm going to want to look at the side that's opposite the angle in question. Well, we already said the angle in question is A. So we're going to locate that angle in question, A, and look at the side opposite that angle and label it opposite. So I'm going to look at this side here. This segment BC becomes the opposite side to angle A. So now what we're going to do is we're going to label that with the pink color. So here's opposite to angle A, okay? And now, because there's always, only 3 sides to a triangle, then what we do is we label the final side, whatever it is. If we've done this correctly, it should always be the adjacent side, and that means next to, if you will. So there's adjacent to A. So now that we have the very base understanding and a review of what SOHCAHTOA means in a very base terms, we can now put the basic ratios together. The sine is the opposite over hypotenuse, right? Sine is opposite over hypotenuse. So we locate the angle that we're looking at, angle A, and we label our triangle. So opposite the right angle, right, is the hypotenuse. So I'll put that. Opposite angle A is little a. Notice how the sides are located? This is opposite to A. And then we can do the last one, which is the adjacent side to A. Now, if you notice how we labeled our triangle, we labeled it big B, angle big B gives us little side B. If we look at angle A, then opposite it is little a. Whoops. And obviously the one that's opposite the right angle, right? Angle C is labeled with a little c. So when we have all these relationships together, we can now actually fill in the remaining components here, here, and here. So let's do that. So what is the opposite side to angle A? Well, that's just A. What's the hypotenuse? Well, that's just C. If you look at the cosine has the ratio or the relationship adjacent over hypotenuse. So the adjacent over the hypotenuse. So now we look at angle A and we look at the adjacent. Well, the adjacent's B, so I just put a little b here. And then we have to put it over the hypotenuse, which is C. Now the tangent we have down here from SOHCAHTOA says that we have the opposite over the adjacent. So let's locate the opposite side. The opposite side is A, and the adjacent side is B. See, we're just substituting the values or variables or even angles in the triangle, and we're going to use these relationships to find lengths and angles within the triangle, the right triangle. So, to recap on how to label a triangle in SOHCAHTOA. SOHCAHTOA is a little acronym that is a relationship that shows the trigonometric ratio right out, the sine, cosine, and tangents. Each one of them has a ratio that they deal with. And that ratio is what is going to define how we work the triangle. And you'll see some more details. So, real quick to review on how to label the triangle. Label hypotenuse first, then go opposite, then do the adjacent. If you do it in that manner, you can hardly ever make a mistake. And that's where it comes, that's what you want to avoid, is making these tiny little mistakes. So now, let's look at our objectives and do some base examples. Okay? The first one that we're going to look at are 3 examples that deal with finding lengths of a specific right triangle using the trigonometric ratios. So it says find the value of x. So again, we're going to go through our basic steps. We're going to label the right triangle appropriately. We're going to start with the red, hypotenuse, then go to the pink, which is the opposite, and then what's left over is the adjacent. So we identified the sides of the right triangle with either values or variables, and we notice what we have. We know the hypotenuse is 21. We know that the opposite side is x, and we know that the measure of the angle in question, which happens to be A, because we're calling it A, why not? Remember, we can just do this, A, B, and C, right? Then that angle A is 31 degrees. We are then going to look at SOHCAHTOA, right? And we're going to select the appropriate trig function, or the trig ratio, and substitute values and variable or variables into and angle into the trig ratio. So whatever we have in the triangle, we're going to substitute within the actual trigonometric ratio. Like the angle will go in for the angle. I mean, we're just substituting the basics. And in this case, when we reference a SOHCAHTOA, since we have both the hypotenuse and the opposite side, which is clear, we know the hypotenuse is 21. We know opposite side is some unknown value, which we labeled x. So we know those two, the hypotenuse and the opposite side. So then referring to SOHCAHTOA, so opposite over hypotenuse, so we would use the sine. And that's why we have it set up as sine of 31 degrees equals x over 21. X, remember, is the opposite, and the hypotenuse is 21. So we just put them in. The opposite over the hypotenuse. That's what the SOHCAHTOA means. Well, that's what the SO in SOHCAHTOA means. So then all we have to do is solve, and that's very easy. We just multiply both sides by 21. And when we do, we get two different representations that we can look for, okay? The first one is going to be the exact solution. This is as exact as we can get. Everything else that's put into a calculator will represent an approximate solution or approximate answer. And what we do have to make sure is that if you are using a TI-84 and you don't know that there are two different measures of angles, then you must make sure, you must make sure that the calculator is in degree mode. Now, that's really easy to do. All you have to do is go to mode, go down, and select degree where it says radian. Now, if you need me to draw that out, please let me know. Inductive and deductive reasoning skills. Number 2, simply find the value of x. So I took a really cheap way of looking at it, right? I look at making math easier, not more difficult. So we did the labeling of the sides. We know that we have an opposite, and we know that we have an adjacent. Those two sides have some kind of substance to it. One is 7 and one is x. So in this case, we know we have opposite and adjacent. SOHCAHTOA, TOA, opposite over adjacent. That's what the ratio is, right? So that's all I did was I took x, which was the opposite, and I divided it by the adjacent. Now, how did I get from this step to this step? Well, no big secret. If I'm dividing by 7 on one side of the equal sign, I need to get rid of it. How do you get rid of a division by 7? Well, if you're dividing by 7, you simply multiply both sides by 7. So all we did was multiply both sides by 7. And again, we have the two solutions, an exact solution and an approximate solution. Notice that this approximate solution is to the tenths. Okay? So remember when a problem might be asked of you, It might ask you to round to the thousandths. It might ask you to round to the hundredths. Make sure you're in the appropriate spot, please. Now, example 3. Find the value of x. Okay, we went through the basic steps again. We looked at SOHCAHTOA. We labeled our sides according to a particular angle. Why did I pick 34 degrees? Because I knew that I could get away easier using the sine than anything else, really. And it was easy to see that the opposite side was 23, and the hypotenuse was x. So what I did was I labeled them appropriately. The hypotenuse with a subscript of 34 degrees. That means that it is the hypotenuse for the angle, if you will, of 34 degrees. And the same thing was done with the adjacent, and the same thing was done with the opposite sides. So now, once we have all that, we just substitute the information into the selected trig ratio. In this case, the sine. So the sine of an angle is, remember, the opposite over the hypotenuse. And then all I did was solve. You'll know how I solved. Well, maybe you noticed the cheat. There's a quick little cheat here, and maybe I can illustrate it kind of basically, or actually I don't even need to show you the cheat really here. This is fine. You can see the cheat later. But the steps involved are multiply both sides by x and then divide both sides by sine 34 degrees. Maybe it is wise just to kind of show you the trick. I don't know if you see it. I was kind of hoping that you'd figure it out yourself, but see if I take this x and I just, move it over here, and I take this sine of 34 and I kind of just move it over here. And then just to clean things up, I move this x just a little closer. You see how those two now are the same? Look at the top red box, the top answer in the red box, and the one we just did. We're actually just switching places because of the inverse operations that are going on. We're multiplying and dividing. So when I put that into the calculator, and remember, make sure it's in degree mode, that you get an answer of 41.1 degrees. Okay. Now, let's move on to the second objective. Let's move on to the second objective. The second objective is all about finding angles. So before we actually begin a very specific example of one of these, let's tell you how things work, right? Because what we know, on just the basic front, right, is this. I mean, no-brainer. The positives, its opposite, are the negatives, right? If I have multiplication, its opposite is division. If I take the square of something, then the opposite is the square root. If I take the opposite of something, I'm getting something back, whether it be 0, 1, or the basic number itself. The point being is looking at the opposites, or the inverses, okay? So what I have here are 3. The first one we're going to look at is the inverse of the sine of A is given by sine to the negative 1. Now, that sine to the negative 1 can be easily found on your calculator just above the sine key. Now, your calculator is built this way for a specific reason. It literally lists what things undo each other, and that's what we're trying to do, is figure out what undoes something, right? We're trying to figure something out. So if they give us a puzzle, we have to work backwards through our inductive and deductive reasoning skills that we learned from Unit 2. Right? We can't just assume that one thing is correct and assume that another thing is correct. But if we made a wrong assumption in our second truthful statement, then we might make a false statement. And that leads us into some troubles, right? It's all about understanding the way we process a particular problem. Now, number 2 simply states that the opposite of cosine is cosine to the negative 1. Now, these are really called arcsine, arccosine, and arctangents, but we're not going to get into that now. 3. The inverse of the tangent of A, or I really should be saying like opposites here for all of these, really. I mean like inverse could mean a few other things too, so just to clarify, I should say opposite, okay? So the opposite of tangent is tangent to the negative 1. Knowing these tells us how to undo the sine, cosine, and tangent. Okay? So when we look at the first example, we'll walk through it slowly. And we'll just kind of peruse through it. So we're going to find the value of x, and then we're going to round it to the nearest degree. So I've already taken the liberty of giving you the problem that we have here that I'm highlighting now. Okay? You'll note that I've already labeled the sides appropriately according to x. So remember, the first step, if you want to think in steps, is to label the right triangle appropriately. Remember, hypotenuse, opposite, and adjacent with respect to the given angle. Then you want to identify the sides and angle of the right triangle with either values or variables. Okay? So what did we know? Or what did we find out? We found out that the hypotenuse was 27. Okay, that's great. We also found out that the opposite side is 11. That's also wonderful. And now we're not given an angle. Notice we're given two sides. We won't be able to do this if we have only one side, right now at least. But what should we also label? The angle in question, and that's what we're trying to find. X, that angle. Okay? So, what do? We're going to select the appropriate trig ratio, and for some reason I keep writing ration, but ratio, and substitute the values and variable and angle into that trig ratio. Since we have the hypotenuse and the opposite side, and referring to SOHCAHTOA, we can see that because we have those two, opposite and hypotenuse, we use SO. Sine is the opposite over hypotenuse. So, that's exactly what I did here. I just did the substitution of all of the information into the process. Now, the next step may look a little bad, but it's not as bad as you may think. Now, let's just see about this. Let's go over here for a second. Okay? So, since the sine and the sine to the negative 1 are inverses or opposites, I should have wrote opposites. Opposites is a better word here to be used. The left-hand side simply becomes x. Well, wait a second. If I take the inverse of something, right, that I'm taking, so it's like if I'm adding 1 to negative 1, I get 0. I get that nothing back. In this case, what we could think about as that nothing is x, and x is what remains. So in order to get rid of the sign, you simply use sine to the negative 1, or technically we should be calling it the arc sign. And if you do it to one side, you must do it to the other. So all I did was take sine to the negative 1 of the left-hand side and sine to the negative 1 of the right-hand side, and came up with the two solutions, the exact and the approximate. Remember which one is which, because sometimes you might be asked what's the exact answer. If they ask that, remind yourself that that's the exact answer. If they look for an approximate solution or approximation, that would be it in question. Okay? So I'm hoping that this makes a little more sense when we put everything together in an example form. Now, example 2. Take a little shortcuts here. Find the value of x, round to the nearest degree. Again, SOHCAHTOA. It's essential to understand SOHCAHTOA. So I look at my angle. I notice that I have an opposite side and an adjacent side. But notice I labeled my triangle appropriately from the beginning. I did this, then I did this, and then I did this. Now notice the color coordination that I'm using too, trying to give you every aspect of seeing what the process is. So now, if you look at SOHCAHTOA here, well, which one of the ratios will it be? Well, we have the opposite and we have the adjacent. That means TOA! TOA, 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 TOA. So that's exactly what I did. I just substituted what information we had into TOA, what it tells us for the ratio. And then, after I did the substitution, well, what's the opposite of the tangent? And again, I really should call this opposite. You know, I'll go fix all that in a second. But if I'm taking the tan negative 1, or the opposite of the tan, so let's just break it down into very basics. I'm taking the opposite tangent of the tangent. Maybe that makes more sense. I'm taking the opposite tangent of the tangent. Maybe that'll clarify it right there. Okay, because inverse could be used for a lot of other different things. So let me go fix that up in a second. So all I did again was take the opposite tangent of the tangent, got my value for x on one side, and if I do it to the left-hand side, I have to take it on the right-hand side. And then you can clearly see that all I did here was, you know, just like I've been doing, I've been putting it into the calculator and receiving this answer here. Okay? So, let me go back and actually fix this a little bit here, because I really don't like the word. I mean, I fixed it here, here, and here. Just before we go in, I just want to... This should be opposite. It's a much better word to use. In my opinion, it'll make things stick out a little bit easier. Okay, third problem. We're going to find, again, the value of x, and we're going to round to the nearest degree. So I've really simplified it, right? Okay. I've labeled the triangle correctly. I've done the color coordinating to show you with respect to the angle x. I then use the cosine, cosine, adjacent over the hypotenuse. So I have the adjacent over the hypotenuse, right? Then I just took the inverse of both sides and came up with my solutions. hoping this is pretty straightforward. Okay. Now, let's get into the application problem that I'd like to work out. And it's a great problem because maybe some people might remember some kind of a similar problem way back when. And that problem was sort of designed around the idea of Mr. Nicholas Copernicus. And he devised a method for determining the sizes of the orbits of planets farther from the sun than Earth. His method involved noting the number of days between the times that a planet was in the positions labeled A and B in the diagram. Using this time and number of days in each planet's year, he calculated C and D. And for our example, Mars has a transitionary of 55.2 degrees, or days, and D has one of 103.8. And I'm going to consider them angles right now, okay? Make it easy, okay? So how far is Mars from the sun in astronomical units, AU, okay? Now, 1 AU is defined as the average distance from Earth to the center of the sun, which is about 93 million miles. So, the setup of the awesomeness. When in doubt, draw it out. I redrew the basic problem and the premise. Notice I labeled things. I labeled, point A for Mars and point B for Mars. Where did it start? Where did it end? I did the same thing with Earth. Where did it start and where did it end? Because we're rotating in this direction right now. So, I then labeled the side, the only side that we knew, because we're assuming that this is 1 AU, telling us that it's 1 AU. We know that there's a right triangle. So now that we have all of this information, what's the one thing we really need to figure out? We need to figure out what this angle is here. And remember back from our angle rules that we can find it very easily because we have the bigger angle and we have the smaller angle, so we can find the unknown angle. So I took it a little further and I redrew it even more basic, okay? I simplified it a little more. The step that I'm talking about now is looking at finding the missing angle, and we're going to call it theta. So this angle is called theta, okay? And what I know is that angle D is much bigger than angle C. So if I want to find theta, all I have to do is subtract C from D. That gives us angle theta, and that's exactly what I did down here. And I gave the approximation to the tenths because that's what they were giving it in to before. So, then I'm not going to talk about significant figures. That's for another class. Then, once I did that, I even simplified it more. You see, you can get a really complex type of problem, right? But it's all an illusion. What your job is to take this really complex problem that I keep highlighting and make sense of it through our language, mathematics, okay? Using inductive and deductive skills, using your general algebra skills and the theorems that we've learned all year. So by drawing it out, I now, let's look at it. Now let's draw a simplified version of our right triangle. Okay? Place our information in place. Remember that we are looking for the distance of Mars to the sun, or the distance, from Mars to the sun. So we're technically looking for this distance x, right? So I labeled it. I gave it some name. I let it have some variable name. In real cases, what I should say is I should say something like, let x be the distance of Mars from the sun. Another way I could have done it was label this point A, for example, right? And I could have said, let angle A be the distance for the segment A, B, Mars. You okay? So there's a few ways we could have said it. Now, again, SOHCAHTOA. Yeah, it's getting to the end of the video, so it's SOHCAHTOA. Okay. So all I did again was insert, right? Substituted the correct values. Now, why did I pick the cosine? Because we have what? The adjacent side, and we have the hypotenuse. And that is the essence. So I used the cosine, and then I solved. Now remember, there is that cheap trick, right? If I take this, I know I'm dividing, and this is a proportion, right? So if I know this, I can multiply both sides by x, and then I can divide, and then I can divide both sides by the cosine of 48.6 degrees. By doing this, I now have calculated the distance needed, which was x. I've given both the exact solution and the approximate solution. I have also given the approximate solution in miles. If you're interested in reviewing that, that's a physics concept, and that's called dimensional analysis. But that's usually taught in physics classes. If you do have any questions about it, please let me know. With that, you can see we're done. So hopefully this clarified or helped you learn the basics of using the trigonometric ratios, the sine, cosine, and tangent. These notes will be posted up on your Google Classroom. And if you have any questions, ask them in the stream first. Then we'll maybe start up a Zoom conversation about what we need to talk about. All right? Thanks, and have a great day, guys. Bye!